Welcome, this is Han Liu from the University of Chicago. In this talk, I will present how out-of-distribution examples and interactive explanations affect human-AI decision-making. This is a joint work with Vivian Lai and Chenhao Tan at the Chicago Human Plus AI Lab. An important research topic in human-AI decision-making is to understand how AI assistants can be used to enhance human performance. Previous studies have found that AI assistance improves human AI team performance compared to human alone. However, human AI teams seldom outperform AI alone. This is observed in a wide variety of tasks, such as deceptive review detection and income prediction. Ideally, with AI assistance, human AI teams should outperform both AI alone and human alone, also known as the complementary performance. It remains difficult to enhance human decision-making in challenging prediction tasks, where AI isn't simply emulating humans. To address the elusiveness of complementary performance, we study two factors: the out-of-distribution examples, an overlooked factor in the experimental setup that enables us to provide a more realistic examination of human AI decision-making when AI suffers from distribution shift. Interactive explanations, emphasizing the importance of two-way conversations between humans and AI, which may promote human understanding of AI predictions. Let's dive into out-of-distribution examples first. We argue that prior work adopts an over-optimistic scenario for AI. Namely, these experiments randomly split a dataset into a training set, sometimes a validation set, and a test set. We hypothesize that this evaluation scheme is too optimistic for AI performance and provide limited opportunities for humans to contribute insights, because the test set follows the same distribution as the training set. In practice, examples during testing may differ substantially from the training set, and AI performance can significantly drop for these out-of-distribution examples. Thus, we propose to develop experimental designs with both out-of-distribution examples and in-distribution examples in the test set. When AI fails in out-of-distribution examples, humans may be better equipped to detect problematic patterns in AI predictions and offer complementary insights. Let's use the task recidivism prediction as an example. The goal is to predict whether a defendant will violate terms of pretrial release given their profile. During training time, the AI model only sees defendants older than 25. During test time, if they are still seeing defendants within the same age range, then this is referred as the in-distribution condition and is equivalent to the typical setup. However, if they are seeing defendants younger than 25 during test time, they are seeing the out-of-distribution examples. This is our proposed setup and is referred as the out-of-distribution condition. Now, let's look at AI explanations. We consider three types of AI explanations with increasing levels of existence. The none-type means no AI predictions nor explanations. This is equivalent to human alone. The static explanations, such as showing AI predictions as well as highlighting important features. Static explanations represent a one-way conversation from AI to humans, and may be insufficient for humans to understand AI predictions. Therefore, we develop interactive interfaces to enable a two-way conversation between decision makers and AI. For instance, we allow humans to change the input and observe how AI predictions would have changed in these counterfactual scenarios. We hypothesize that interactive explanations improve the performance of humans and their subjective perception of AI assistance's usefulness. Okay, here we derive three research questions with the two factors I just introduced. First, how does distribution types affect performance? We evaluate performance by measuring the gain of accuracy of human AI teams over AI alone. Second, how does distribution types affect agreement? We measure agreement as the percentage of examples where human AI teams give the same prediction as AI alone. Third, how do interactive explanations affect human AI decision-making? We will discuss both performance and agreement, as well as subjective perceptions. We conduct both virtual pilot studies and large-scale human experiments by crowdsourcing. After instructions and attention check, participants go through a training phase, then a prediction phase, and finally complete an exit survey. We adopt a two-factor design with distribution types and explanation types. In explanation types, we allow different interfaces in the training phase and in the prediction phase. For example, the condition interactive none means that participants see the interactive interface in the training phase, but receive no assistance in the prediction phase. We adopt this design because ideally participants should be able to learn enough to achieve complementary performance with less or even no assistance after the training phase. Now let's look at the results. We plot the results for performance in this figure. The vertical line at 0 means the zero accuracy gain of AI alone over itself as the baseline. We observe that for in-distribution examples, human AI teams underperform AI alone. For out-of-distribution examples, human AI teams do not outperform AI alone with statistical significance, but the accuracy gain is positive in several conditions. It follows that the performance gap between human AI teams and AI is smaller for out-of-distribution examples than for in-distribution examples. This confirms that humans are more likely to achieve complementary performance for out-of-distribution examples. We summarize the results for agreement into two observations. Agreement for in-distribution examples is higher than for out-of-distribution examples. This suggests humans behave differently depending on distribution types, and on average, trust AI more for in-distribution examples, as we expect. Interestingly, agreement with wrong AI predictions is lower for out-of-distribution examples than for in-distribution examples. This can be observed from the striped bars. The yellow striped bar tells us for all in-distribution examples where AI makes a wrong prediction, human AI teams make the same mistake 19.7% of the time, even higher than the 86% agreement in the correct prediction case. However, for out-of-distribution examples, the red bar shows that human AI team only make the same mistake 76.7% of the time. This suggests humans may be better at providing complementary insights into AI mistakes for out-of-distribution examples. We are only presenting the interactive condition here, but the observation is consistent across all explanation types. Last but not least, we find that interactive explanations do not lead to improved performance of human AI teams, nor lower agreement with wrong AI predictions. However, they significantly increase human perception of AI existence's usefulness. Participants with interactive explanations are more likely to report real-time assistance useful in the exit survey. We also conduct an exploratory study on what features participants find important in recidivism prediction. We find that participants with interactive explanations are more likely to focus on demographic features and less likely to identify the computationally important features. For example, with interaction, participants are more likely to find race useful for prediction. However, it is not the most important feature based on Spearman correlation. Meanwhile, they make more mistakes when they disagree with AI. These observations suggest that interactive explanations might reinforce existing human biases and lead to suboptimal decisions. In summary, here are 4 takeaway messages from this work. First, we proposed a novel setup demonstrating a clear difference between in-distribution examples and out-of-distribution examples. Second, evaluation on performance and agreement shed light on the promise and importance of exploring out-of-distribution examples. Third, by enabling a two-way communication, interactive explanations improve human perception of AI existence's usefulness. Finally, despite a design intention to help users, interactive explanations may reinforce human biases and lead to suboptimal decisions. Thank you very much for listening.